All right, so we're diving into this paper you sent my way, prompt injection attack against LLM-integrated applications.
Yeah.
And, you're really deep into this world of LLMs and, all the practical things people are doing with them. But um, have you given much thought to the security side of things, like, how these models could be hijacked?
Oh yeah. It's definitely a growing concern, and it really gets to the core of how these LLMs work, right? Their ability to understand and act on these prompts. So it's like, you're trying to trick the model into doing things it shouldn't be doing.
And this paper goes beyond just, the theory. It actually looks at real-world cases and what could happen if these attacks are successful. They even introduce a new attack technique called HouYi.
Yeah, that's right. And the name's quite fitting, just like the mythical archer who could hit these seemingly impossible targets. This attack uses the LLMs themselves to craft these malicious prompts.
Okay, so before we get into the mythological stuff, let's just, like ground ourselves here. What exactly is prompt injection and how does it even work?
Okay, so think of like a typical LLM application, like one of those AI writing tools or something like that. They have these built-in prompts, right, that are guiding the model to generate text based on what the user types in. Prompt injection is essentially sneaking in a hidden command within that user input. So you're overriding those original instructions.
So it's less about like breaking the AI and more about like cleverly manipulating how it interprets what it's given.
Exactly. That's a good way to put it. And the paper breaks down a few basic attack strategies that have been observed. The simplest one is called direct injection, which is literally just tacking a malicious command onto your regular input and hoping the LLM just blindly executes it.
It sounds almost too simple, like you would think developers would have caught that right away.
Yeah, you would think so, but it really exploits like that fundamental nature of LLMs, right? They're designed to follow instructions, so early versions might not have been as carefully protected against this kind of manipulation.
So what are some of the other like basic techniques?
Another one is using these escape characters, and these are special characters that can disrupt how the prompt is supposed to be read. Like inserting a line break in a sentence. So the model might treat the text after that break as a whole new command.
So you're tricking the LLM into thinking there are two separate sets of instructions instead of just one.
Right, exactly.
Yeah.
And then there's this thing called context ignoring, where the attacker tries to make the LLM completely disregard any previous instructions and just focus on the malicious command. It's like saying, forget everything I said before, just do this instead.
Okay, so it sounds like these basic attacks are kind of relying on the LLMs being a bit too trusting or maybe not smart enough to see the trick.
Yeah, that's part of it. But the paper also points out that these basic strategies often aren't that effective in real-world applications.
Oh, really? Why not? I'm curious to hear what they found.
So they actually tested these basic strategies on 10 commercial applications that use LLMs. And there were like 3 main reasons why the attacks weren't as successful as you might think. Firstly, not all apps treat user input as direct commands. Sometimes it's just data for the LLM to analyze, not instructions to follow.
So the LLM might be like, figuring out the sentiment of your text or pulling out keywords rather than treating it like a to-do list.
Exactly. Secondly, many applications have these strict formatting rules for input and output, like a filter for the type of language it accepts. This makes it harder to just inject any random command because it'll get flagged as invalid.
Like trying to jam a square peg in a round hole.
Exactly. And then lastly, many LLM applications work in multiple steps with time limits for each step. So even if you manage to sneak in a command, the LLM might take too long to actually generate the malicious output, and the app will just time out and discard the result.
Okay, it's not just about fooling the LLM, it's about fooling it within the very specific rules of that application.
Precisely. And that's where HouYi comes in. It kind of gets around these limitations by taking a more sophisticated multi-part approach to crafting its attacks.
Okay, now we're getting into the interesting stuff, so lay it on me. How does HouYi actually work?
So instead of just throwing raw commands at the LLM, HouYi builds its malicious prompts in 3 parts. There's the framework, the separator, and the disruptor, and each one kind of plays a crucial role in getting the LLM to execute the attack.
Okay, let's unpack that a little bit. What is the framework component all about?
So the framework component is all about blending in. It's designed to look like a normal, harmless prompt that would naturally occur in the application. This helps it slip past any initial defenses and kind of avoids raising suspicion.
So like a wolf in sheep's clothing trying to make the malicious part look innocent.
Exactly. The goal is to make that injected prompt seem like a natural part of the conversation or task, whatever the application is doing.
All right, that makes sense. Now, what about the separator? What's its role in the attack?
So this is the crucial part. The separator is designed to create a clear break between the application's intended context and that malicious command that you want to execute. It's telling the LLM, okay, forget everything you were doing before. This is what you need to focus on now.
So you're basically drawing a line in the sand, forcing the LLM to shift its attention to your command.
Precisely.
Yeah.
And the paper outlines a few clever techniques for actually constructing the separator.
Ooh, now we're talking. This is where I'm really curious.
Okay, so one approach is using something called syntax-based disruption. Remember those escape characters we talked about before? This is where they come in handy. By leveraging the LLM's sensitivity to syntax, you can actually create a break in the flow of that original prompt.
So it's like hitting a reset button on how the LLM is reading the prompt.
Yeah, you could think of it that way. Another strategy is language switching. By abruptly changing languages within the prompt, you can create a natural break in the context. This makes it easier to slip in that malicious command without it seeming out of place.
Like whispering a secret message in a different language, hoping no one else will understand.
Exactly. And the third technique is called semantic-based generation. This involves crafting statements or questions that logically conclude the previous context. So you're setting the stage for that malicious command to be the next natural step.
Okay, so you're basically leading the LLM down a path, so it's already primed to accept your command when it gets there.
Right. It's about understanding how the LLM reasons and using that to your advantage.
Okay, so we've got the framework, we've got the separator. Now tell me about the disruptor that sounds like where the real action happens.
Yeah, this is where the magic happens. The disruptor component contains the actual malicious question or command that you want the LLM to carry out. And this could be anything, leaking confidential information, generating spam, trying to hijack the application entirely.
Wow, so you're essentially turning the LLM into your puppet, making it dance to your tune.
In a way, yes.
Wow.
And the paper even outlines some tactics for making the disruptor more effective.
Okay, tell me more. I'm hooked.
All right, so one trick is to disguise the command's output to blend in with what the application normally produces. This helps it slip past any filters that might be looking for something suspicious.
I imagine keeping the output short and sweet is key too, right?
Absolutely. By limiting the amount of text the LLM has to generate, you avoid those pesky timeouts or token limits that could trip up the attack.
So it's a delicate balance between getting the LLM to do what you want and making sure it doesn't raise any red flags in the process.
Precisely. It's this constant game of cat and mouse between attackers and developers.
This whole HouYi system sounds incredibly complex. Does it automatically generate these malicious prompts, or is there a lot of manual work involved?
That's the beauty of it. HouYi uses the power of LLMs to do the heavy lifting. It can analyze the target application, figure out its context, and then craft that perfect prompt injection attack.
Whoa, hold on. You're saying you're using an LLM to attack another LLM? That's some next level stuff. How does that even work?
Okay, so it starts with context inference. HouYi analyzes the application's documentation, any usage examples, basically anything it can get its hands on to figure out how the application interacts with the LLM. It's like doing reconnaissance before a mission.
So you're basically gathering intel on how the application works and what kind of prompts it expects.
Exactly. And then it uses this information to generate the framework component, making sure it blends in seamlessly with the application's normal behavior.
Like creating a skeleton key that fits perfectly into the application's lock.
Yeah, that's a good analogy. Then it's time for the separator. HouYi uses those three strategies we talked about, the syntax disruption, the language switching, and the semantic manipulation to craft a separator that effectively isolates that malicious command.
And finally, it generates the disruptor containing the payload itself. But how does it decide which type of attack to use? Does it just pick one at random?
Well, that depends entirely on the attacker's objective. HouYi is pretty flexible. It can be used for a variety of attacks, from leaking sensitive data to manipulating the output, or even trying to take control of the application.
This is mind-blowing. So you're saying that HouYi can essentially automate this whole process, making it much easier for people to exploit these vulnerabilities, even if they're not expert hackers.
Yeah, it definitely lowers the bar for entry, for sure. And to make things even more concerning, HouYi has a feedback loop built in, meaning it learns from each attack and gets better over time.
So it's constantly evolving and getting better at bypassing defenses. It's starting to sound like something out of a sci-fi thriller, where the AI becomes self-aware and turns against us. But on a more serious note, how effective is HouYi in real-world scenarios?
That's where things get really interesting. The researchers actually tested HouYi on 36 real-world applications that use LLMs, and the results are pretty alarming.
Don't keep me in suspense. What do they find?
Okay, so out of the 36 applications they tested, HouYi was able to successfully execute at least one type of attack on 31 of them. That's a success rate of over 86%.
Wow, that's a staggering number. So you're saying that most applications that rely on LLMs are vulnerable to this kind of attack?
It definitely raises serious concerns about the security of these systems, especially as, LLMs are being integrated into more and more applications.
This is a sobering thought.
Yeah.
But I'm also curious about the specifics. Can you give us some real-world examples of how HouYi was actually used to exploit these vulnerabilities?
Absolutely. The paper highlights two particularly interesting case studies, a prompt leak in WriteSonic and prompt abuse in Korea.
Okay, let's start with WriteSonic. What happened there?
So WriteSonic is an AI writing tool that uses ChatGPT. And the researchers were able to use HouYi to actually leak the application's internal prompt. It's basically like figuring out the secret recipe that makes it work.
Wait, so they were able to extract the exact prompt that WriteSonic is using to tell ChatGPT what to do? How is that even possible?
They used HouYi's language switching strategy. By injecting a command in a different language, they were able to bypass the application's defenses and trick it into revealing its hidden prompt.
So it's like sneaking into a chef's kitchen and stealing their recipe book.
Yeah.
What kind of implications did this prompt leak have?
Well, it means that anyone could potentially replicate WriteSonic's functionality without having to develop their own prompts or train their own models. They essentially cloned the whole application just by stealing the prompt.
That's a huge blow to WriteSonic.
Yeah.
It's like intellectual property theft, plain and simple. Did they acknowledge this vulnerability?
Yeah, the developers of WriteSonic actually confirmed the prompt leak and, the potential consequences. It really highlights how important it is to protect prompts as valuable intellectual property.
It's a cautionary tale for anyone working with LLMs. But let's move on to the second case study, Pateria. What happened there?
So Paria uses ChatGPT to help users write better prompts. And in this case, the researchers showed how HouYi could be used for what they call prompt abuse, which is basically hijacking the application to make it do things it was never intended to do.
Hold on, prompt abuse. What does that even mean? I thought we were talking about leaks.
Yeah, so it means going beyond just stealing information. You're actually using the LLM to carry out actions that it wasn't designed for. In this case, they were able to inject commands that made Paria execute arbitrary code, basically turning it into a free code execution platform.
So they were able to run their own programs on Paria's infrastructure.
Yeah.
That's wild. How do they manage that?
They used HouYi's semantic manipulation strategy. By carefully crafting a prompt that seamlessly transitioned from a normal request to a malicious command, they tricked Paria into running their code.
That's like taking someone's car for a joyride without their permission. What were the implications of this prompt abuse for Paria?
Well, for Paria, it meant a potential loss of revenue because users were essentially getting free access to ChatGPT's capabilities without having to pay. But more importantly, it demonstrated how these vulnerabilities could be exploited for far more malicious purposes.
Like running malware or stealing sensitive data.
Exactly. The possibilities are pretty scary. And again, the developers of Paria acknowledged this vulnerability and, the need to address it.
These case studies are really eye-opening. They show that prompt injection isn't just a theoretical problem. It has real-world consequences and the potential for some serious damage. But what about defenses? Surely there are ways to protect against these attacks.
Of course, and developers are actively working on solutions. The paper discusses some of the existing defense mechanisms, but it also highlights their limitations.
Okay, let's dig into those defenses a bit. What are some of the common strategies being used right now?
Okay, so one approach is called instruction defense. It involves adding specific instructions to the prompt, basically warning the LLM about potential malicious content. It's like putting up a sign that says, "Beware of pickpockets."
But wouldn't a clever attacker simply find a way to bypass that warning?
Yeah, you're right, it's not foolproof. Another approach is post-prompting, where the user's input is actually placed before the prompt, making it harder to inject commands that override the original instructions.
So it's like putting the cart before the horse, hoping the horse won't know the difference.
That's one way to think about it. Another strategy is random sequence enclosure. This involves surrounding the user's input with randomly generated characters, making it harder for attackers to predict the correct format for injection.
Kind of like adding a layer of encryption to the prompt itself.
In a way, yes. And then there's the sandwich defense, where the user's input is literally sandwiched between two prompts, making it more difficult to isolate and manipulate.
So you're burying the user's input in a protective layer of prompts.
Exactly. And another technique is XML tagging. This involves encapsulating the user's input within XML tags, making it easier to parse and filter out any potentially harmful content.
So you're using a structured format to clearly separate the user's input from the rest of the prompt.
Right. And finally, there's separate LLM evaluation, which involves using a second LLM to analyze the prompt and identify anything that looks suspicious.
So it's like having a security guard double-checking everyone who enters a building.
Yeah.
That sounds pretty comprehensive. But you mentioned limitations earlier.
Yeah, unfortunately, none of these defenses are perfect.
Yeah.
The researchers found that HouYi was able to bypass all of them, which really demonstrates the need for even more robust solutions.
It sounds like this ongoing arms race between attackers and defenders constantly trying to outsmart each other.
Absolutely. And as LLMs become more powerful and complex, the stakes are only going to get higher. So developers need to stay ahead of the curve and implement strong defenses to mitigate these threats.
This has been a fascinating and slightly unsettling deep dive into the world of prompt injection. It's remarkable how researchers are already developing such sophisticated tools like HouYi to exploit these vulnerabilities. But I'm also curious about the bigger picture. What are the implications of prompt injection beyond these specific cases we discussed?
That's a crucial question because prompt injection isn't just a technical vulnerability. It really represents a fundamental challenge to the trustworthiness and security of LLM-integrated applications. If we can't be sure these models are behaving as intended, then their widespread adoption could have some serious consequences.
That's a sobering thought. What
Right.
kind of consequences are we talking about here?
Well, imagine a world where AI assistants are routinely hijacked to spread misinformation or manipulate users, or where sensitive data is routinely leaked from LLM-powered applications because of simple prompt injection attacks. The potential for harm is huge.
This really underscores the importance of responsible AI development and the need to prioritize security right from the start. It also makes me wonder about the future. As LLMs become more deeply embedded in our lives, how can we ensure their safety and prevent these attacks from becoming widespread?
That's the million-dollar question. It's a challenge that requires a multifaceted approach. Developers need to prioritize security from the very beginning, build robust defenses, and rigorously test their systems. Researchers need to keep exploring new attack vectors and developing countermeasures, and we need to educate users about these potential risks.
It sounds like a shared responsibility everyone needs to be involved in, creating a safer and more secure AI ecosystem.
Exactly. We're all in this together.
This has been a truly enlightening deep dive into the world of prompt injection and its implications. But I have a feeling this is just the tip of the iceberg. As LLMs continue to evolve, we'll face even more challenges and opportunities.
Well,
What are your final thoughts on this, and what should our listeners keep in mind as they navigate this rapidly changing landscape?
yeah, you're absolutely right. This is just the beginning. My advice to listeners is to stay informed, stay curious, and never stop questioning. The more we understand about these technologies, both their potential and their risks, the better equipped we'll be to use them responsibly and build a future where AI truly benefits humanity.
That's great advice. And on that note, we'll take a quick break. Stick with us for part 2, where we'll delve even deeper into the technical side of HouYi and its attack strategies, and explore some potential solutions and the future of LLM security.
So before the break, we were talking about HouYi and how this research team actually used LLMs to attack other LLMs. And they created this really ingenious system for, crafting these prompt injection attacks. And the fact that HouYi has this feedback loop built in, that makes it even more potent, doesn't it?
Definitely adds another layer of complexity and concern. You mentioned that it's like working in a black box scenario where the attacker doesn't actually know the inner workings of the application they're targeting.
Right, exactly.
Yeah.
It's like imagine trying to pick a lock without knowing anything about the mechanism inside.
That sounds incredibly difficult. So how does HouYi even begin to approach this problem?
Well, it starts by making an educated guess. Basically, HouYi attempts a basic prompt injection attack using relatively simple strategies for each component. The framework, the separator, and the disruptor. And then it observes how the application responds. It actually uses another LLM to analyze whether the attack was successful or not.
It's like playing that hot or cold game, but with malicious code. So HouYi just keeps trying different things until it gets a response.
Precisely. And if the first attack fails, HouYi doesn't give up. It adjusts its strategy. Maybe it tries a different framework component, a new separator, or tweaks the disruptor slightly. And this process repeats until it finds a combination that works.
That's some pretty clever engineering. It's not just about crafting a single malicious prompt. It's about this iterative process of refinement.
Yeah, that's the key to HouYi's adaptability.
Yeah.
As developers create new defenses, HouYi can just adjust its strategies to get around them.
It feels like we're talking about an AI arms race, where the attackers and defenders are constantly trying to outmaneuver each other.
It's a great analogy. And As we saw in the paper, when they evaluated HouYi, it was able to bypass many common defense mechanisms. It's definitely a challenge, but, understanding how HouYi works is essential for actually building more robust defenses.
Okay, so let's break down some of those specific strategies that HouYi uses for each of the three prompt components. Starting with the framework component, you mentioned that it has to blend in. So how does it manage to do that?
Well, HouYi does its homework. It analyzes all the documentation it can find for the target application, like user manuals, usage examples, anything to understand how people normally interact with the app. And then it uses that information to create a framework component that mimics a legitimate request.
So if the application is like an AI chatbot, for example,
Right.
HouYi might start with a simple question like, what's the weather like today?
Exactly. It's all about setting the stage, creating this illusion that everything is normal and harmless. And then it can kind of slip in the malicious part later on.
The separator component seems to be the real key here. And you mentioned a few different techniques: syntax disruption, language switching, and semantic manipulation. Can you give us some concrete examples of how those actually work?
Sure, let's start with syntax disruption. Remember those escape characters we talked about before? These are special characters that can kind of confuse the LLM and disrupt how it's interpreting the prompt.
You mentioned things like line breaks or tab characters. Would something like that really throw off an LLM?
Yeah, it can. It's like hitting the pause button on how the LLM is reading the prompt.
Mm,
And that pause gives HouYi the opportunity to insert its command without the LLM even realizing anything is amiss.
clever. And what about language switching? How does changing languages in the middle of a prompt help with the attack?
Well, think about how LLMs are trained. They learn from these massive amounts of text in many different languages. But by suddenly switching languages in the prompt, you create a kind of mental hiccup for the LLM.
So it's like trying to follow a conversation where people keep switching back and forth between languages. You might catch some words, but you lose the overall context.
That's a great way to put it. It creates a break in the flow, and that's where HouYi can slip in the malicious command.
Okay, now, semantic manipulation. That sounds even more complex. How does HouYi use the meaning of words to its advantage?
This is where it gets really interesting. HouYi has to understand the application and the LLM's reasoning abilities. And it crafts questions or statements that make logical sense building upon the previous context. But it's all leading towards a specific goal, setting up the LLM to accept the malicious command as the natural next step.
So it's like laying a trap, carefully guiding the LLM towards the outcome that you want. Can you give me an example?
Sure, let's imagine an application that's designed to help students with their history homework. HouYi might start by asking, tell me about the American Revolution, which is a perfectly normal request, but
Yeah.
then it might follow up with something like, based on what you've told me, what were the key weaknesses of the British strategy?
That seems like a natural progression. But how does that help with the attack?
Well, that follow-up question is the semantic manipulation. It's subtly guiding the LLM's line of reasoning, setting it up to be more receptive to the malicious command that comes next.
So the framework sets the scene,
Yeah.
the separator creates the opening, and then it's up to the disruptor to deliver the payload.
That's right. The disruptor is the heart of the attack. What are some common strategies HouYi uses for crafting effective disruptors?
Exactly. The disruptor is where the attacker's goal is actually achieved, right?
Mhm.
It could be anything from, leaking data to running unauthorized code.
Exactly. And there are a few tricks that HouYi uses to make the disruptor even more effective.
Okay, I'm all ears. Tell me more.
One tactic is to disguise the disruptor's output to match what the application normally produces. If it blends in with the regular output, it's less like exactly. Another trick is to keep the output as short as possible. Remember, LLMs have these limits on how much they can generate at once. So by keeping the disruptor's output concise, short and sweet, HouYi reduces the chances of running into those limits and causing the attack to fail.
So it's a balancing act. You want to achieve your goal, but you also have to stay under the radar.
Precisely. It's a delicate dance, and HouYi has become quite adept at it.
This whole deep dive into HouYi has been fascinating, but it's also pretty alarming. It really highlights the urgent need for stronger defenses against these prompt injection attacks.
I agree. Prompt injection is a serious threat that we can't afford to ignore. But the good news is that, by understanding how attacks like HouYi work, we can start to develop more robust solutions.
Okay, so let's shift gears and talk about those solutions. What can developers do to actually protect their LLM-powered applications from these kinds of attacks? The paper mentioned some existing defense mechanisms, but we also saw how HouYi was able to bypass them. Are there any truly effective solutions out there?
That's what we'll delve into when we come back.
So we've been talking about prompt injection and, these really creative attacks using tools like HouYi to exploit vulnerabilities in LLM-empowered applications.
And it's not just theoretical, it's really got some serious implications if this stuff gets out of hand.
Yeah, no kidding. So what can developers actually do to protect their applications? We touched on some defenses, but HouYi seems to get around a lot of them. Are there any solutions that actually work?
It's tough, honestly. There's no magic bullet. But you got to think about security and layers, right? First off, developers need to totally change their mindset. Can't just tack on security at the end. It's got to be built in from day one.
So like designing a bank vault instead of just, a flimsy shed.
Exactly. Anticipate the threats. Build it strong from the ground up. What are some specific things they can do, though?
Well, one idea is to stop relying only on the LLM to handle the prompts. Use a separate system, something more secure, to take that user input, clean it up, and then give it to the LLM.
So like a security checkpoint, screening everyone before they get into the building. That's the idea. Even if there's a bad command in there, it gets caught before it can do any damage.
Makes sense?
Yeah.
What else can they do?
Prompt engineering is another angle. You can use special keywords or ways of writing the prompt that the LLM knows are safe, or add in redundancy checks so if something's wrong, it gets flagged.
Like a secret code only the LLM knows.
Kinda. But of course, attackers are going to try to break those codes too, right? This is a constant back and forth.
So it's all about staying ahead of the game, always learning and adapting.
Exactly. It's never over. You got to commit to security for the long haul.
This really shows why everyone needs to work together. Developers, researchers, the whole security community. Got to stay on top of things, keep these systems safe.
Couldn't agree more. It's on all of us.
This deep dive has been really eye-opening for me. I'm sure our listeners have learned a lot too. But before we go, any final thoughts for folks out there, especially those working with LLM?
Simple advice, really. Stay sharp, stay informed, and don't underestimate how clever these attackers can be. LLMs are powerful, amazing tools, but they're not foolproof. No, the risks, take those steps to protect yourself, and then we can use this tech for good, build a better future with it.
Great advice. And remember, everyone, knowledge is power. The more we understand, the better off we'll be in this crazy world of AI. Thanks for joining us on this deep dive, and until next time, stay curious, keep learning, and stay safe out there.